Okay, well, this is almost finished here, then we will go ahead and get started. Um, I've actually am recording this lecture, so I hope to post it on, I'll probably stop about 45, 60 minutes into the lecture and then just start a new recording. So we'll probably be taking a little bit of a break about halfway through that there. I actually tried to do this before class started, but it should be close to finish here. Installing. All right. Well, I'm going to go ahead and get started. I'll finish up this installation later. That there. Okay. I'm just going to basically pick up where we left off. Right there. And right now, both my classes, my microcontroller and microprocessor class, are running in parallel. We're going to be deviating probably starting this week. That there, because I haven't put together a detailed week-by-week syllabus for this class where I go through I guess you call that, a statement of work or, that there. And the reason is that making such major changes in the way this course was taught last time versus the way I've taught before, I'm not sure where it's going to end up. So we're going to kind of swing it there. So I'm going to continue with a little basic background. This really should be first part of today should still be review of digital, that there. And then we're going to get more into microprocessors and microcontrollers as the hour goes on, that there. So, all right, these are just some terminology that there. You're going to see the term bit. That should be a very familiar term to you. That's a 1 or a 0. That's a single binary digit. That there. You will hear the term byte. Byte is a very common term, and that is simply 8 bits. An 8-bit word, or an 8-bit byte, and I'll use the term word somewhat interchangeably with byte, although they do mean something different, will represent the numbers from 0 to 255, right there. So when we talk about microprocessors and microcontrollers, you'll hear the term an 8-bit microcontroller or an 8-bit microprocessor. That means that the internal registers of that microprocessor are 8 bits wide, right there. The data bus is 8 bits wide, right there. So if you hear the term 16-bit, it means that it's actually a word wide, right there. And modern microprocessors are now 64 bits wide. The first microprocessor was actually 4 bits wide, which is a nibble, right there. So I don't know. It's kind of ironic, the choice of words between bit, nibble, and byte, that there, and then we jump to something completely different, and that's a word. It should be a gulp or something like that there, because the first three evolve around food, and then eating, and then we go to a word. And what's not shown here is there's the double word, which is 32 bits, and the quad word, which is 64 bits. So they're not on this table. But those are the terminologies that we look at there. The next thing there, and this is IBM PCs and compatible, so this is every computer. You'll hear the term a kilobyte. When you look at metric notation, and that's easy in Malaysia because we've got latecomers sneaking in here, that there. So in Malaysia, you typically have you use the metric system, so you think in terms of kilometers and kilograms. When I taught this course in the U.S., some students have never used the metric system. So then the terms kilo, mega, giga, terabyte aren't quite as common, although all the engineering courses and everything in electronics and electrical all use the same notation out there. However, when we go into the digital world, it changes slightly. A kilobyte is it's 1,000 bytes, but that's not quite the same as if you look at a kilobyte of memory is really 1024, So it's not really 1,000, it's 1024, it's 2 to the 10th. Same thing with megabytes. It's not quite one, it's a little bit more than 1 million right there. So, and same thing with gigabyte and terabyte, they're not quite the same. So sometimes that causes some confusion when people do computer upgrades, that they buy especially with hard drives, because they'll list something as a 30 gig drive, and what the manufacturer on the sales brochure will say it's 30 gig, although that's a tiny drive by today's standards, so I'll still use that example. And you go to format it, and Windows will say that it's 28 point something else. That's because the manufacturer is saying, 30 billion memory location or locations, or 30 billion bytes of data that it will store, but they're using billion. Windows is using the 2 to the 30th. So they're not quite the same. They're off by roughly 5 to 10% up there. So that does cause some confusion when you work in the computer area, in the digital, because the term kilobyte is not 1,000 bytes in this class. It's 1024 bytes. Same thing with the term megabyte is 10 to the 20th, not 1 million. So it's a little bit more than a million. It's 1,224 out there. So it's off by that little bit. And I actually have seen people go on to forums and they buy a hard drive from. In the U.S., we have a company called Amazon and Newegg. Here you got what? Lazada, is that there? But I don't see where people write reviews of products here. Is that a common thing here? But people will buy a hard drive from, say, Newegg, a company, and they format it, and Windows says it's something different than what the hard drive is. And it's just basically because they're not familiar with the fact that 30 gigabytes to Windows is 30 times 2 to the 30th. 30 gigabytes to the manufacturer when they write the sales brochure is 30 billion, which is less than 30 times 2 to the 30th right there. So you get some discrepancies, and don't worry about it. It's not going to be placed anywhere, but you just need to be aware that they're not exactly the same when you, for example, if you take a course in electronics and you're talking about frequency, 2 gigahertz is 2 billion cycles per second. It's 2 billion. It's not it's nothing else. In other words, that's a gigahertz is 1 billion cycles per second right there. So same thing when you talk about distance. 30 kilometers is 30,000. 30 kilometers is 30,000 meters right there. So they're a little bit different, and it does get a little bit confusing. I don't know that there. All right, now we're getting into the area that's a little bit new. I said a little later in this hour. Now we're later in the hour right there. And we're talking a little bit about a microprocessor system. The CPU is the central processing unit right there. When we talk about a processor system, that is usually the microprocessor itself. Now, it drives me nuts when people refer to this as the CPU. This is not the CPU right there. I'm pointing to the computer underneath the desk there. That's a full computer. That's got everything in it. The CPU is just the microprocessor chip. That's there. So, there. It executes information stored in memory. What the CPU is going to do is we give it a set of instructions, and it does the instructions one at a time. Right there. We tell it to move data from one register to memory, it does that. We tell it to add two numbers together, it does that. We tell it to multiply two numbers together depending on the processor, it will do that. We tell it to divide two numbers, it will do that. We tell it to take data from one memory location and move it out to the outside world, it will do that. It does one instruction at a time. We write instructions for it, and it does that there. It's a form of it's a digital circuit there that executes instructions. So actually what it is, it's a very large finite state machine. And I know in your digital class they mentioned that word, but you probably didn't design too many of them up there. But it's got, state number 1, get the instruction. State number 2, get the data required for the instruction. State number 3, execute the instruction. And we're going to be going through that process, how that works as the semester goes on. We've got 2 types of memory that we're going to be dealing with up there. One is ROM. The term ROM is somewhat fuzzy today. These terms change. I'm using slides from an older book, which the books we're using are a little bit older. The term ROM basically means read-only memory. You can't write to it. It's non-volatile. You turn the computer off. It's still there the next time you turn it on. But most of the ROMs today are reprogrammable. Right there. That's there. An example of what used to be a very fixed type of ROM, and everybody in this room's not old enough to remember, but I'll just kind of go back and talk about that there. The early motherboards, there's a part of the computer that you can get to. It's called the BIOS. It's the basic input-output system that's there, and it's stored on the motherboard. Out there. When the computer is designed, there's a chip on there that contains the basic firmware, and you'll hear the term firmware used a lot in this class. Out there, firmware that contains what the computer is supposed to do when you turn it on. It's supposed to go out. It's supposed to read the hard drive. You can tell it which hard drive to read. You can tell it various things. Back in the early days of computers, that was fixed. You couldn't change that. So what computer geeks had to do, and I was back in the early days of computers, they had a bunch of jumpers on the board where you have to go through and tell the computer how much memory is in there, and you would move the jumper there. You would tell it how many drives there are there. You would tell it which drive to boot into. That there. You would do that all, by moving, and this involved taking the cover off the computer, getting a flashlight down there. I always had a flashlight that, I looked like a coal miner looking into that there, and a pair of needle nose pliers because I got big fat fingers, and move these little jumpers around, right there. And you sit there with a manual. All right, I just bought another, 32K of RAM, so now I've got 64K of RAM, so I need to move this jumper to this location, right there. So you could not change the BIOS. That was fixed when you bought the motherboard. It did not change at all. Today, when you boot up a computer, you can hit a button there that says Setup, right? Where you can go through there and you can tell it how to configure your hard drives, how much memory you've got, and that's all done in a little software program that this motherboard manufacturer wrote called the BIOS, the BIOS manager. It might be called something else when you look at the screen, but you see that. And you change all that in software. So what used to be fixed in stone out there, in the early days of ROM, you could buy ROM in 2 flavors. One was programmable, and there's what they call OTP. You programmed it once, and if you made a mistake, you threw the chip away and you did it again. That was usually OEM manufacturers would buy those because they were cheaper than the next type, which was erasable at there. And the way we used to erase those is you put them underneath a tanning booth type light, although in Malaysia you don't need tanning booths out there. The sun's bright enough here, right? But it's an ultraviolet light that you shine on that to erase the chip. That there. And then you could reprogram the chip and plug it in there. So those there, or you had the masked ROMs, which the manufacturer would make for you with the whatever code you want. So that's why it's called firmware, because you could change it once, but you couldn't change it thereafter. That was the ROM out there. But the BIOS is on your computer. You have to go into a special program to write to it. When you turn the computer off, unplug it, don't use it for 6 months, whatever you last put in there is still there. Right there, it's still there. So it's non-volatile. The term non-volatile means it doesn't disappear when you turn it off. If you screw it up and you write the BIOS in such a way that the computer won't boot up, there's usually a little jumper where you can go in there and jump it back to the defaults that there to where you can boot it up and reconfigure it. So that's a type of ROM that we still call it ROM, but it's not really ROM in the term ROM anymore. So as I said, some of this terminology gets confusing. That's probably why some of you probably struggle with this class, is that this is the digital world, microprocessor world, changes faster than anything else in electronics, in the electrical world. This course, by the time we finish this course, it'll be obsolete. Actually, even if this course was 100% up to date, by the time you graduate, everything in this course would be obsolete. That's there. So you know, keep that in mind. So my goal is to teach it to you one time, and you learn enough where you could read up on the next generation. That's there. Because there's no way that I could tell you about a microprocessor that's going to be released 3 years from now. It's not, you know, it's not even on the drawing board yet. They introduce new ones every 6 months. That's there. And besides, the newest ones are so big and so powerful that I don't keep up with how to work them on this level. That's there. So, okay, the other type of memory is RAM, random access memory. These terms are so confusing. I hate this term. That there. I hate the term RAM, because random access means that you can randomly access any memory location within the chip. Well, ROM is a random access. You can access any memory location. When we look at how memory is configured, ROM and RAM are configured to the microprocessor exactly the same way. The only difference is in normal operation, we can't write the ROM. So ROM is a correct term. Random access is not a correct term. They're both random access. But this is memory that we can read to and write to. So this is read-write memory. Is a much better term for that there. But everybody refers to it as RAM. You've got a laptop computer, you want to make it faster. It's got 2 gig of RAM. You go to the computer store and say, I want to buy more RAM. They pop out your 2 gig chip module. They put in a 4 gig chip module. Now all of a sudden your computer's faster. That's there. So that's there. So this term RAM is really kind of misleading. It's read-write memory. We can read to it and they write to it. We address them when we look at the circuits that we design to access this type of memory. We're going to find that they're the same. They use the same address lines. They use the same data lines. The only difference is there's a line that goes from the microprocessor to the memory called read-write not. When it's high, it's a read. When it's low, it's a write. That's why it's called read-write not. And that's written, let me get my pen here, right here. Is it because I started later, is this seems to be going faster today. It looks like right there. But you'll see something that looks like this, read/write not, right there. That's what I mean by read-write not, right there. This is a control line. It goes from and we'll talk a little bit more about this. It goes from the microprocessor to the memory chips. When it's high, we're reading the memory location. So what we're asking is the memory to take whatever's in the location and put that out onto the data bus so we can look at it. And we'll go into more detail. When it's low, we're asking the memory chip to look at what's on the data bus and put that into that memory location that's addressed. That's there. And we're going to go into a lot more detail, and this all sounds like I'm talking a third language here. That's there. So what you're stuck with is an American speaking English, now speaking computer geek language. So now we've introduced a new language here. That's there. And we're going to be seeing a lot of this new language, and that's really where this whole subject tends to get very muddled, is that like engineering itself's got a lot of new terms, and then when you go into the digital world, we have another set of vocabulary. So those are the two types of memory that we've got. The top one is input-output. That's looking to the outside world, right there. So input-output When we're dealing with a computer, usually means things like interfacing to a mouse, to a keyboard, to a printer. A hard drive is actually an input-output device. It's a storage device. From the CPU standpoint, it's an output, and you have to write a program to talk to it, various things. That's there. So we're not going to do a lot. We're not going to be doing anything with hard drives, writing and reading from them in this class. It's beyond the scope of this course. That's there. So we've got. So that's actually a third type of memory that's not discussed here. We'll talk a little bit about that, and that's storage. Storage has multiple forms, anything from flash drives, SD cards, hard drives. Can't think of anything else off the top of my head. Usually if you plug in your phone, it looks like a storage device as well. That's there. But these are the types of that there. We used to have floppy drives and tapes. Fortunately, the tapes have gone away. That's there. My first real computer actually came with 2 cassette tapes that plugged into the front of it. That's there. So if you want, the software was on one tape and the data was on the other tape. And these were high-speed data tapes. They weren't cassettes like you would play in the car. But everything was on a tape. There was no hard drive. Hard drives were too expensive at that time. That's there. So there. Hard drives really didn't become, 1980, probably about 86, 87 before hard drives became affordable for the home user. Out there. I mean, that's ancient history to you, but to some of us in this industry, that's not. And let me just throw this out. When you look at other things in the electrical world, between 1986 and today, we're talking. We'll say 85 today. That's 30 years, right? Power generation hasn't changed, right? You still basically have a generator that you have to turn a shaft that moves the conductors through a magnetic field. That hasn't changed. Motors hasn't changed. Power distribution lines hasn't changed. Way you can do power factor correction, that hasn't changed. What has changed? Communications. Why has televisions changed? They didn't change for 50 years, really. The first TVs came out in the 1940s. Colors came out in the 1970s, about 30 years later. And then nothing really changed in television till about 10 years ago, 15 years ago. And what changed? This changed it. Computers. Digital. They went digital. That's what changed television. That's there. Prior to that, if you go back to an old analog TV, and I know some of you still had them. We went to a workshop at an old hotel that had the old analog TV with the vacuum tube in it. And I know everyone's seen those, right? That's the same basic TV that I bought in 1975. That TV hasn't changed from 1975 till about 2000 to 2005. Then the flat screens came up. The flat screens are all digital. Some of you are smiling there. You still got some of those around the house? That's there. That's there. So, but the digital, as I said, the one area of electronics and electrical that has changed has been the digital world. And the change in the digital world has affected other parts of it. Cell phones were big, nasty, big tanks when they were analog cell phones. Now look at the size of a cell phone. How big is it? What does it do? What's the difference between a phone you buy, an Apple iPhone 6 versus the old Nokia that was analog, that was this big, and all it did was make phone calls? What's the change? It's gone digital, right? You've stuck a computer in there, right? A microprocessor. That's there. That's the change. And now you're running. And there's a lot of people that ask the question: Is a cell phone a embedded device where you stick a microprocessor in it, or is it a computer that happens to make phone calls? I will go out on a limb and say it's a full-blown computer system that makes phone calls. That just happens to be one of its many functions. It has a word processor, has an email program, it has this, it has that. Oh, by the way, it also has a phone app. That's there. You know, so it's not really, you're not really buying a phone, you're buying a handheld computer system. That's there. All right, sidetrack. This is a horrible slide. I'm going to skip this slide. It didn't copyright, but basically this is supposed to be the computer. This is the address bus or the data bus and the address bus. I will draw that by hand here and kind of give a clearer picture. Actually, I think there's a clearer picture on that there. Right there. Okay, this is a much better picture. This is the picture that I want to address right here. This is the way things work overall right here. This is a basic CPU microprocessor system right there. Right there. This could be any microprocessor out there. Now, some of these things, like the RAM and ROM, might be sucked inside the same IC, but from a standpoint of seeing what's happening, it's still the same. The CPU is what controls everything. It's got 3 buses. And when I talk about buses, these are not the ones you take from here to Johor Bahru. These are a group of lines. A bus typically will have a number of bits attached to it, and we'll just kind of look at here. Let's say we look at the address bus. It may have the lines A0 through A15. This is 16 lines or wires that connect between there. This is the data bus. This may be D0 through D7, or it may be D0 through D15, D0 through D31, depending on whether it's 8-bit, 16-bit, or that there. When we talk about the control bus is actually a series of control lines, and they are not numbered the same. You know, in other words, the control bus will have things such as address latch enable. We'll get into what that means. I already talked a little bit about the read write not line. It may have another line for synchronization. These are 4 or 5 lines that control the flow of communications. There may be an I/O/memory not line. So are we talking to memory, or are we talking to an input-output device? So this is the way that this is connected. Now notice my last discussion, the RAM and the ROM are connected exactly the same. Right there. It's just that some of this here, we can't change on the fly. This we change on the fly all the time. This is our disk. Now our disk is controlled to that, but it actually looks like a I/O device to the system. The monitor, I don't necessarily like this because the monitor and the keyboard are not tied directly to the bus. They're usually tied to some interfacing hardware as well. This is a very general graph. The monitor actually has to go through a graphics card, and the graphics card has to go through the instructions on how to do things. We're not going to be getting to that level. Same thing with the keyboard. Actually, this particular device right here, is this doing anything? The keyboard in front of your computer actually has a microprocessor in it itself. It has an 8051 actually, or a version of the 8051 inside of it there, because it's got its own software to talk to. So it's almost a computer within itself. When you hit a key, it sends communicates back to the computer system. But this is the basic thing. And I was looking at the final for this class from last semester, and about a third of the questions involved in the final from that class, and probably that there, is how do we wire all this up? What do those wires mean? What memory locations are addressed? What I/O locations? So this is the hardware side, and that's a little bit more where this class is going to reside out there. So this is what we've got. But these are the 3 buses that we talk about: address bus, data bus, and the control bus. There's other buses that will pop up, but those are the 3 biggies right there. The address happens to be just what it is. If you live on, say your address is 55 Jalan 3/29B, Kuala Lumpur, it's the location of that memory location right there. That's there. The data bus happens to be what's at that address. It may be your house, it may be whatever, right there. In the case of microprocessor, it's a number. The only thing that's stored at these memory locations are numbers, but these numbers can represent, other numbers. They can represent pictures. They can represent text. They can represent everything. Everything is represented by a bunch of numbers. So this is the typical inside organization of. I'm going to lose this thing here. Right there. So, okay. All right. This is just kind of a little bit more detail, and again, I'll be posting these in there. The address bus is unique to every device. So there's actually, you'll hear the terminology mentioned I/O mapped I/O and memory mapped I/O. When we look at memory locations, they go from 000 to F, depending on how many lines there are in the address bus. The microprocessor we're going to be using has a 16-bit, has a 20, well, it's a 16-bit microprocessor we're going to be using for the lab, but when I go through and talk about the 8086, it's got a 20-bit address bus. Now, the size of the address bus will determine how much memory a particular microprocessor can address. Right there. So if you look at, say, an 8086 and 8088, it's got 20 address lines. So if you take 2 to the 20th, that means that particular microprocessor can address about 1 million memory locations, 1 meg of memory. 2 to the 20th is 1 meg, which is 1024 locations, a little bit more than a memory. If a microprocessor has a 16-bit address bus, it can address roughly 64K or 65,336 locations or something like that there. But the size of the address bus determines how many memory locations you can address right there. The size of the data bus determines how much data can be at each of those locations. There, if it's an 8-bit microprocessor, it's going to have an 8-bit data bus, which means every one of those 65,000 locations is going to contain a single 8-bit number. If it's a 16-bit microprocessor, every one of those 16,000 locations is going to contain a 16-bit number. And same thing if we go to a 32-bit microprocessor. So it basically goes through, and you look at those two numbers, they go somewhat, the size of these buses determine a lot as far as, the larger the data bus, I like to look at it as a highway. You take the old highway between KL and JB. I think it's called Highway 1 or whatever. Of course, I know in Malaysia you don't use highway numbers, right? That there, but but everyone knows the little highway that goes through every town right there. You see it. That's there. That's a little 2-lane road for most of it. So you got 1 lane of traffic in each direction. You look at the north-south highway. It goes from the same location to the other. It's 3 lanes across. That's there. Some places it's 4 lanes across. That's there. Obviously, traffic moves much faster. So the wider the data bus, the more data you can move in and out of the processor at a time. That's there. So the control bus is just basically to control things. You look at it as the stoplights and the signals in between. You tell devices to stop, wait until I'm done with the bus, and then you can have it at there. Because the address bus, let me just point out, with few exceptions, the only one that writes the address bus is the microprocessor. That's the only, he's the only one. He controls the show. He's the only one that can write to the microprocessor. The data bus is bidirectional, and it's very tricky when you deal with the data bus because every memory chip, every I/O chip, and the processor all can write to the data bus. Obviously, they can't all write to the data bus at the same time, because then you end up with smoke coming out of your computer system or out of your microwave oven where the digital control board is, or out of your phone. Bad things happen when 2 devices write to the same bus at the same time. So that's really where the control is. But the control also tells memory, when it's time to latch the data in, when is the time to put data onto the bus. It also controls the timing of everything. So those are the 3 buses that we deal with. We're going to be spending a fair amount of time looking at these buses and how they interface from IC to IC. Right there. Matter of fact, I'll probably, let me take a quick little break here, and I'm saying about 2 minutes where I, 3, it's probably going to be more. Oh, I hate this thing. I have to keep, I'm sitting here pushing buttons wanting things to happen, and they don't happen. Oh, I have to do it from here. That's all right. I have to stand in front of this right here. Okay. I know that that's a setting that I can find, but I haven't found it. That there. Keep changes right there.